Now, forces that govern the universe. There are four fundamental forces that I want to talk about, and there's only probably a couple of them that are terribly important. But we can say that all forces are divided up into one of four types, and three of these forces actually probably are different manifestations of the same force. And the fourth one, physicists have not yet been able to unify that force with the other forces. But it's highly likely the fourth force is also the four forces. The weakest force is gravity. Although it can be, you've got a very, very massive object and another massive object, and they're in proximity to one another. That seems like that's a pretty tremendous force. But actually, if we were looking at this in terms of two particles that were near one another, the magnitude of the force would actually be very weak. The next, sometimes it's called the weak nuclear force. Then there is electromagnetism, electromagnetic force, and finally the strong force and strong nuclear force. So we've seen with gravity that the force diminishes as you move out by the square root of the distance that the two objects are from one another. That's how the force will diminish. So it's inversely proportional to the square of the distance. That's also true of the electromagnetic force. So these two forces have that in common. There are particles or vectors that actually mediate these forces. The photon is the particle that would actually carry the electromagnetic force. The strong force is carried by something called the gluon. Gravity would be carried by a particle that no one has yet observed, but it's a theoretical construct called the graviton. And the weak force is mediated by three what are known as vector bosons. And the bosons are designated Z, which is a neutral boson, and then there's a positively charged W plus and a negatively charged W minus. So the weak force. This is the force that mediates radioactive decay. So when something is radioactive and one element is giving off beta particles and gamma radiation, it's the weak force that's actually determining that. And the strong force is actually the force that's holding nuclei together. In the nucleus of an atom, you've got positively charged particles, and you've got in the larger atoms, you also have neutral particles, you have neutrons, and then the positively charged particles, so you have something like that. And two positively charged or more positively charged particles would actually have a tendency to, because of the electromagnetic force, these two things are actually repelling one another. So they ought to want to fly apart. But the strong force is much stronger than the electromagnetic force, and the strong force is holding them together. But the strong force has a very short distance over which it operates. It's only effective at 10 to the minus 15 meters, so a millionth of a nanometer. So we're talking about once two of these particles get separated by a distance greater than that, then the electromagnetic force is actually going to become stronger than the attractive strong force, and those things would tend to fly apart. So I wanted to illustrate this because it's important for understanding why such high temperatures are required in order to initiate thermonuclear reactions, fusion reactions, because in a fusion reaction, what I want to do is I actually want to take a proton and another proton and push them together, fuse them together in order to form a new atom. So I want to take the nuclei of hydrogen atoms, which are just protons, and the reason that these are nuclei is because at the incredible temperature inside the sun, and even at temperatures much lower than that, the electrons would have been promoted to E infinity. That is, they would no longer be actually bound to the atom. So you've got essentially a plasma, and you've got electrons, and you've got protons that are just floating around. But these protons, they have to overcome this kind of repulsive effect that we would get from the electromagnetic forces. So if they're heated to a sufficiently high temperature, they're going to have enough kinetic energy that these two things can actually smash into one another. Once they do that, then the strong force can take over. So if I can get enough energy to actually get them to come together, they will unite. When two protons combine, one of them is actually going to change into a neutron. Now I want to go back to, just briefly, the idea of beta decay, so you can sort of understand what's going on here, because in beta decay, which as I said is mediated by the weak force, what happens there is that a neutron actually turns into a proton. So when you have atoms that have an excess of neutrons, too many neutrons, one of them can turn into a proton. It does so by emitting an electron. The electron didn't really, it's not like the electrons that actually surround atoms. I mean, it's the same kind of particle, but I don't want you to think that a neutron is nothing more than a combination of a proton and an electron. It's not. But what happens is that a neutron can turn into a proton, and when it does, it ejects the excess mass in the form of an electron. So it's not like there's an electron hiding in there. The electron doesn't exist until this process occurs. So it's also possible to go in the other direction. And this happens with certain elements where there's actually a deficiency of neutrons. There's too many protons for the number of neutrons. And in that case, what will happen is a proton will turn into a neutron. And when that happens, there's another particle called a neutrino that is emitted, and also emitted from the positively charged electron, which is called a positron. So those things actually are what we call positron emitters. In the other situation where we have a radioactive element that's decaying, like the element tritium, which is a form of hydrogen, which has, this is the way that we designate tritium. It's telling us that it's got an atomic number of 1 and an atomic mass of 3. So that indicates that there's 1 proton and a total of 3 particles, which means that there have to be 2 neutrons in there. That's the difference between 1 and 3. And what's going to happen is one of those particles is going to convert from a neutron into a proton. So now we'll have 2 protons down here, and that is the atomic number of helium. So this becomes an atom of helium, but we still have the same mass, which is that. Although this process actually occurs spontaneously, what we've done is we now have an atom of helium, and that's going to produce an electron. So the electron is designated this way, -1, and the reason for that is because 2 minus 1 is 1. That's its atomic number. The mass is 0, so 3 plus 0 is 3, and 2 minus 1 is 1. So that has to balance out. And then there's another massless particle, which is, in this particular case, is an antineutrino. We use a slash over the symbol to indicate that it's an antiparticle. And this is a beta particle. So the other way to write that is a beta particle. If I wanted to show this as a positron, that is a positively charged electron, then I would have written this as +1 E0. It has to do with quarks changing, because protons are actually composed of 3 quarks. 2 of them are called up quarks. So a proton has 2 up quarks and 1 down quark. And that's the positively charged proton, 2 down quarks and 1 up quark, neutron. So this is the neutron. And so what's actually happening here is that when these kinds of events occur, when a neutron changes into a proton, basically what's happening is a down quark is converting into an up quark. And these things have fractional charges. So the up quarks have a charge of +2/3, and the down quark has a charge of -1/3. So you can see if you've got 2/3, that's 4/3. 2 of these minus 1/3 equals 1. And here we've got 2/3 minus 1/3 minus 1/3 equals 0. So the neutron has no charge, and the proton has a charge of +1. Anyway, getting back to the fusion process. So if we have enough energy to overcome this, I want to write these reactions now, not the way they're shown in your book, but using this designation, which actually makes it a little bit easier to understand. You've got basically a proton, which is hydrogen, and you've got another proton, and these 2 things come together, and they form something called deuterium. Deuterium is nothing more than 2 hydrogen atoms. When they do this, though, when these things fuse, they give off I mentioned before that this out of balance. So you notice it wouldn't balance. There's got to be a 1 here and a 0 here, and that's a positron. So you can see that this balances out. So we have 2 atomic numbers of 2 here, atomic numbers of 2 here. 1 plus 1 is 2, 2 and 0 is 2. So this balances out perfectly. So this produces this, and it also produces a neutrino. So here's our neutrino. That's the Greek letter nu. And this is the positron here. So now we've got deuterium. So now deuterium can fuse with another proton. So in the next step, deuterium is going to fuse with a hydrogen atom, and that's going to give us this unusual isotope of helium that I showed before, which is this helium-3. So this is not part, this is a separate thing. This is not part of this process. This is just the way tritium actually converts into helium. Tritium can convert into helium-3. But deuterium and hydrogen can fuse at these very high temperatures, and they can also give helium-3. So when they do that, now we've got 3 here. So we don't really need anything because we've got 2 and 3. So we're going to get a lot of heat out of this, but we're just going to form helium-3 in this process. Now the next step, which is going to be the fusion of 2 helium-3 nuclei. Helium-3 plus helium-3. That doesn't give us 4 and 6. Instead, it gives us helium-4, which is the normal isotope of helium. But then we get 2 actually protons at that temperature. So now we've got 6, 4, 5, 6, and 2, 4, 2, 3, 4. So that balances out, and this kind of completes the cycle for us because it's giving us these 2 more hydrogens, these 2 more protons that we need to go back to the beginning of the cycle. So there's one other thing that's taking place, because we have to be able to account for everything that we see that's coming from the sun. There's also a significant amount of gamma radiation. So where does that come from? And also, why don't we see any positrons? Because positrons are actually being produced in the first step of this reaction. We're getting positrons, but we don't actually see any positrons. Well, it turns out that positrons, which we could call a form of antimatter, or at least it's an antiparticle. Remember, in the plasma, we also have a lot of electrons. So we've got all these electrons that are flowing around, and when a positron and an electron interact with one another, they actually annihilate one another. So the mass, although small, totally disappears. There's no mass left at all. And what happens is a positron plus an electron, they come together, and basically what you get are 2. That is the Greek letter gamma. And you realize again that that's going to be 0 and 0. This is a photon. It actually has no mass at all. You actually produce 2 photons. So when these 2 things come together, you get 2 photons, one particle and antiparticle are hitting this way. The photons are going to be emitted at right angles, so you'll get a gamma photon going in this direction, and another gamma photon going in that direction. And each of them will carry away half of the energy equivalent of whatever these particles' masses happens to be. So that actually completes the entire process, and it is that process that's actually driving the sun. There's one little problem with this whole thing, and that is when astronomers actually sat down and looked at this and calculated the number of neutrinos. Now, the neutrino is an extremely small particle and very, very difficult to detect, because on average a neutrino, even if it's formed in the core of the sun, can pass right through the sun without ever interacting with anything. And if you had a thickness of lead that was several light years in thickness, that it's possible any individual neutrino might be able to make it all the way through that lead without ever interacting. But neutrinos do, even though it's very rare, they do interact with matter. So people had to find ways of detecting them, and they use things like gallium, which is a metal that has a little bit more affinity for neutrinos. So they had vast quantities of gallium that they could use as detectors. The idea being that when a neutrino actually hit these things, it caused a flash of light that could be recorded. There's also other processes where they use either water or possibly deuterium oxide, and I think that also involves a scintillation, a flash of light that can be detected. In the case of gallium, it's not a scintillation, it's just a photon, probably a gamma photon that's being produced, and they can actually record that. But nevertheless, you can have this go through lots of water, so deep underground, to prevent there from being other kinds of cosmic ray types of particles that would interfere with the experiment. They set up huge detectors, and maybe 1 out of 10 to the 15th or something like that, which is 1 out of a quadrillion neutrinos that actually enters this detector might actually get detected. So the experiments take a very, very long period of time, but eventually a certain amount of neutrinos are actually detected. And what scientists found was, if everything that I've told you so far is true, that the number of neutrinos that should have been impinging on the Earth was 50 to 70% fewer neutrinos reached the Earth than are theoretically predicted. This, for many years, was known as the neutrino problem. So the neutrino problem was finally solved not too long ago when it was discovered that neutrinos have an unusual aspect to them. There are three kinds of neutrinos. Now, I told you that there were other subatomic particles. There's a collection of particles that are called hadrons, and these are things like protons and neutrons, mesons. These things are all composed of quarks. So the hadrons are made of quarks, and there are different kinds of quarks. The ones that compose matter are these up and down quarks, which are designated as U and D. And you can also have the antiparticles, anti-U and anti-D, anti-up and anti-down. And then you've got other particles that are called top and bottom. And these names just are designations. They don't really have any physical significance. It's not one of them is on top of the other one. And then there's two others, abbreviated C and S, which stands for charm and strange. And the names are strange too. And then the antiparticles. Well, with neutrinos, we have different kinds of neutrinos as well, and they also have antiparticles. So we have one neutrino which is associated with the electron. This is what we see in atomic decay, and it's called an electron neutrino, designated by nu sub e. And then there's also a nu sub mu, which is called a muon, and a tau neutrino, which is nu sub tau. It looks like that. Well, it turns out that what is believed to happen is that these electron neutrinos emanating from the sun, in the 8.5 minutes or so that it takes for them to reach us, they actually undergo what are known as neutrino oscillations. A neutrino oscillation, when that happens, one kind of neutrino actually changes into another kind of neutrino. So some of these things might have been oscillating into maybe tau neutrinos or muons or whatever, and because of that, they weren't being detected in the experiment. Chapter 17, giants, dwarfs, and main sequence stars. If you could reduce the sun to the size of a marble, so something like about this big, and then put this down on the floor, and then set down a grain of sand about 1 meter away from that marble, that would represent approximately to scale the difference in size between the Earth and the sun, and also the distance between the two of them. So that 1 meter now is an astronomical unit. If you're thinking in terms of meters now, that means that everything in our solar system would lie no more than 30 meters away from that marble. If we wanted to then plot on this same scale the next nearest star to us, which is Proxima Centauri, then we'd have to go out another 270,000 meters, 270 kilometers away in order to reach that star. So we're talking about now 270,000 astronomical units, how much further away that is than the sun is from us. So we're talking about really enormous distances. So now, in order to find these kinds of distances, we have to use stellar parallax, which is basically the same process. It's just that, remember that with parallax, the further away something is, the smaller that parallactic angle is going to be. And if you don't have a pretty big baseline, it's going to be smaller still. So it turns out that if you're trying to see something as far away as Proxima Centauri, which is the closest star to us outside of the sun, so far away, 4.32 light years is approximately, well, light year is about 6 trillion miles. So looking at something that's more than 25 trillion miles away from us. And in order to be able to see that, if that's such an enormous distance, and you've only got the Earth, which is just a few thousand kilometers across diameter, if you're on one part of the Earth or the other part of the Earth, your baseline to that star is still going to be extraordinarily small. However, if you realize that the Earth is rotating around the sun, and for instance, I can take a day of the year, like say summer solstice, I'm at one position, and then I can look at the winter solstice, and if I examine, since now the sun is over here and the Earth is rotating around it, I can actually have my baseline becoming 2 astronomical units now, because it's 1 astronomical unit from here to here, another astronomical unit from here to here, and now it's possible for me to be able to triangulate and to find, by knowing that angle and doing a little elementary trigonometry, I can easily then calculate the distance from me to that star, from the Earth to the star. So that's basically what's done. And what you have to do is, in order to get the parallactic angle, what you're doing is you're looking at the motion of that star, how that star appears with respect to much deeper background stars. So this thing is going to move a certain position across the sky. And from that, it's possible to determine the parallactic angle. So it turns out that we have something called a parsec, which is the parallax expressed in arc seconds. So remember that there are 360 degrees in an arc, in a circle, and then there are 60 minutes per degree, and then there are 60 seconds per minute. So that means that there's 3,600 seconds in a degree. So 1/3600th of a degree is equal to 1 arc second. And at that distance, if its parallax was 1 arc second, its distance would be 1 parsec. A parsec, which as I said before, is parallax in arc seconds, but a parsec is equal to approximately 3.3 light years, and that would be roughly on the order of about almost 20 trillion miles. So Proxima Centauri is 270,000 astronomical units away, or 4.3 light years. The distance in parsecs would be whatever 4.3 divided by 3.3 is. But the way you find the distance in parsecs is you take 1 over the parallax in arc seconds. So you have reciprocal of that. 1 over the parallax in arc seconds equals the number of parsecs.